Hello and welcome back. This week we're going to be looking at the Gauss-Jordan method for solving general systems of equations. And we've looked at Gauss-Jordan before, and now we want to look at this a little bit more in depth. So first we need to discuss reduced echelon form. So a matrix is going to be said to be in reduced echelon form, or simply reduced form, if any row of all zeros is at the bottom of the matrix. So any row of all zeros must be at the bottom. The leftmost non-zero in each row has to be a 1. This is called the leading one of the row. And the leading one of any row is to be to the right of all leading ones above it. This is to the right. Okay. And all entries above and below a leading one are 0. So essentially what we're doing is making the first non-zero entry in each row into a 1, and then using that to pivot and clear all values above and below the 1 in that column. And then we'll just organize the rows so that our 1s are descending on the diagonal. So let's look at these examples down here. Are any of the following matrices in reduced echelon form? Well, let's look at the first one. Any rows of all zeros are at the bottom. Well, we don't have a row of all zeros, so we're fine. The leftmost non-zero in each row is a 1. Let's see, the leftmost is a 1, is a 1, is a 1, so we're okay here. The leading one of any row is to the right of all the leading ones above it. Well, let's look. The rightmost leading one is to the right of all the ones previously, and the same is true for the second and the first one. And then all entries above and below a leading one are 0. And we can see that that is true because we have zeros above and below. So below the first leading one, above and below, and then above the final and third one. So all of these matrices are in reduced echelon form. The first matrix is in reduced echelon form. So the first one we get, yes, this is reduced echelon form. Let's take a look at the second one. The bottom row is all zeros. The first non-zero term is a 1. That's good. Do we satisfy the organization? So are the 1s organized in descending order on the diagonal? Yes. And let's see. We have zeros above and below each leading one. Yes. So this second matrix is also reduced echelon form. And now let's look at the third one. Let's see. Any row of all zeros is on the bottom. Well, that's not true because we have a row, the third row, which is all zeros, and that one should be on the bottom. Also, notice that this second column, we have a leading 1, but we have a non-zero in that column. So this also violates rule number 4 for reduced echelon form. Similarly, the column 2 and column 3, those are in the wrong order because the leading ones need to be to the right of all leading ones above them. So the leading one that we're seeing in this bottom row actually needs to be before the leading one that we see in this second row. So we would need to switch our rows, interchange them so the order is all correct. So this is not in reduced echelon form. Alright, so the whole point of getting a matrix into reduced echelon form is so that we can read the solution for the system of equations that the matrix represents easily from that matrix. So let's look at an inconsistent system. An inconsistent system is one that has no solution. If you have a row in your augmented matrix that is entirely 0 except for a non-zero in the right-hand column, then that's what we call an inconsistent system. So remember, the augmented matrix, we really have a vertical line right here. The rightmost column is always the constants or the constraints column. So our first column here is representing, say, variable x1 and then x2 and x3. Okay, and then the rightmost column would be our constants. So if we want to solve this system using Gauss-Jordan, we're going to need to get a leading one in each row and pivot on each leading one so that we can get it into reduced echelon form. So let's see, the first row we already have a 1 in the leading position, and we have zeros below it. So column 1, row 1, this is all good. So now we move down to the next row. So in row 2, we need to make the 2-2 position into a leading 1, so then we can pivot and eliminate the 4 and the -13. So in order to do this, we will need to create a 1 in the position that has a -13. So we will do 1 over -13 times row 2. And this is just to give us a 1 in that first position of the second row. So let's see, if we do this, row 1 and row 3 remain unchanged. So row 1, we have 1, 4, -2, and 13. Row 2, everything was divided by -13. So we get 0, +1, -10 over 13, and we get 33 over 13. And in the bottom row, we get 0, -13, 10, and -30. Okay. So now that we have this leading 1, we can go ahead and try to pivot on the second column in order to eliminate the 4 and the -13. So we're pivoting off of this leading 1 that's in the second row in order to change the terms in row 1 and row 3. So let's see, for row 1, we're going to need -4 times row 2, because we always use the opposite of the constant that we're trying to eliminate. And then we will add this to row 1, and this of course goes into row 1. And in the bottom row, we will have +13 row 2 plus row 3, and this will go into row 3. So after doing these row operations, we get the following matrix. So we will have the first row becomes 1, 0, 14 over 13, and the constant would be 37 over 13. The second row stays unchanged, so 0, 1, -10 over 13, and 33 over 13. And the third row becomes 0, 0, 0, 3. So this is where we see something interesting happening. In the third row, we have non-zeros entirely on the variable side, and then we have we have zeros entirely on the variable side, and we have a non-zero on the constant side. Well, remember, each of these columns is representing a variable. So what this bottom row really says is 0x1 plus 0x2 plus 0x3 somehow has to equal 3. But 0 plus 0 plus 0 is just 0. And so now we have 0 equals 3, which doesn't make sense, right? Because 0 and 3 are not the same. 0 is not equal to 3. And so this is why we know this is an inconsistent system. And so this would be a system of equations that has no solution. Okay, so we can now say that this is inconsistent, and so our solution is no solution. Now you may be thinking, this seems maybe like a lot of work to figure out that you have no solution. So let's look back at the original matrix that we started with. I'm just going to go ahead and erase this right here. Notice that row 2 and row 3 are almost identical. Row 2 and row 3 are exactly the same in column 1, column 2, and column 3. The difference is that their constants are different. So at this point, we can also say that this will be an inconsistent system. And the reason being, if we interpret each row as an equation, we'll see that we have the same equation equaling different numbers. So if we interpret row 2 as an equation, this gives us -13x2 plus 10x3 equals -33. And if we interpret row 3 as an equation, we have negative 13x2 plus 10x3, the same thing that we had in the first equation, but now it's equaling negative 30. So we can't have the same equation equaling two different values, and so this tells us that we are inconsistent. So there's multiple ways you can determine if you have an inconsistent system. If you ever see two rows that are identical on the variable side, so on the coefficient matrix, but they have different constants in the last column, then you can automatically say the system is inconsistent. Or if you don't notice that, then you'll be able to tell you have an inconsistent system once you get to the end, because you'll have a row of zeros with a non-zero constant on the other side. So a couple different ways we can determine if we have an inconsistent system.